All righty. So I hope everybody's doing all right today. I want to talk a little bit about forces. So let's start with the screen share. Oh, it should be there somewhere. There it is. Okay. A lot of what we have been doing this semester is to get us ready for this exciting moment where we talk about forces. Now, forces are vectors with magnitudes and directions. And so, again, everything that we have done so far, maybe it's kind of gotten lost in the shuffle, but we're trying to make sure you're good at dealing with vectors and all the math associated with it and all the details associated with getting vector problems right, like the unit, sig figs, and all that stuff too. But forces are vectors, which means just imagine you have a ball sitting here. You could imagine gravity is going to be one force acting on it. And that could be represented by a magnitude, say mg, and a direction, in this case, downwards. Maybe there's a drag. Maybe drag points this way. So we could call that some force just drag. Maybe there's another force. Maybe there's a thrust force. Maybe this is an airplane or something. So maybe we just call that with some magnitude T or something. Or you could say it has a different magnitude. But the idea is you could imagine this is a lot like chapter 3 where you have vector problems and we add them up. Furthermore, oops, let me get out of this for a second. I need a little more space there. We already know something about acceleration and coordinate systems, just a little bit. A lot of times we assume X is to the right and Y is up. So why don't we just keep assuming that? Maybe this thing is accelerating in some other direction. The acceleration, as you already know, is a vector. And here's kind of the short version of this. Let's say you want to predict where something will move. Remember, the word move relates to velocity, which is related to acceleration by kinematics. And so, lo and behold, the idea here is I guess the big picture is we're going to try and relate pictures of objects with all these complicated forces on it, as shown in the green circle here. Okay. And that will relate to the acceleration vector, which we could then use to model the motion of a particle. And in the real world, life is really complex. Forces can change over time. And so the acceleration can change over time. And then, so I guess the next level up would be you use a computer to calculate what the forces are at any one given moment. And then you use that same calculation to calculate the acceleration at any one moment. And then you calculate the velocity at any one moment and then move the object for a small increment in time. Then you repeat the process. You recalculate the forces based on its new position. Did it stretch a spring more? Is there more or less speed? Is there more or less air resistance? Is the thing running out of gas? Is there less thrust over time? All kinds of different things could happen, but that's the short version. We can use forces, and this will be the final piece to model a great number of applications. So that's just kind of a reason why you should care about this. We're so close to doing stuff that actually matters instead of just playing with numbers all day and playing with units all day and looking at equations and thinking this is silly. So we're close, people. So that said, again, we're going to try and figure out these pictures of forces, use that to figure out the accelerations, and then in theory, you could use kinematics to do something with it. So before I go on, any questions about that? You could throw it in the chat. You could ask Jay at any time, whatever you want, or you could just unmute if you want. That's our big picture. Before you could, and at any time, interrupt me if I cut you off too soon, okay? Now, before we get ahead of ourselves and start doing these full complicated problems that I just spoke of, we need to learn some of the basics a little bit better. So below, I have a list of common forces. We'll kind of skim that. And every book is a little bit different. So I just put this in there so you get used to using my book. I try to be consistent with my symbols, and every book is a little bit different. That said, the symbols I plan to use are down here. The units for force are newtons. And notice that a Newton is a kilogram meter per second squared. Now, what I like to do is I remember that the gravitational force near Earth's surface is mg. Well, m has units of kilograms because we have that. That's just a mass. And g has units of meters per second squared. So rather than try and remember what a Newton is that way, for some reason, I just have it stuck in my mind. Well, I know forces are equivalent to mg's in terms of units. So the units of force are the units of mg, which are kilogram meter per second squared. This is a mass times an acceleration magnitude. All right, so there's the units of the force. Okay. Now, for me, notice something subtle here, and I just do this because the fewer subscripts I have to write, the faster I can write my notes. I want to point out that a Newton, the unit of force for a Newton is a capital N. That's the unit of force. Okay. Sorry, I'm a little slow here. And then this lowercase n is the magnitude of the normal force. Now, normal, I'm not saying like I'm a completely normal guy kind of normal, or you're abnormal because you're taking this class. I'm saying normal as in perpendicular. So in a math class, normal means perpendicular. Okay, so that's what I mean by normal. I mean the mathematical definition, I mean perpendicular. So I'll just write perp here for perpendicular. Okay. Now, a normal force acts everywhere. Let me go through a couple of these. The first four of these are kind of the big ones that we're going to be using, and we use friction in the next chapter, chapter 6. But so these ones right here, the first three are kind of the most important. Normal force, tension, and gravity. We're going to use those a lot in this chapter. So tension would be like the force from a cable or a string. Now, to be clear, N with the vector over it would be the normal force vector. N with no vector over it is the normal force magnitude. So be aware that there's a difference between a vector and a magnitude. Similarly, T, the tension vector, is not the same as tension magnitude. So hopefully I've been pretty careful with this in the book and the solutions and your test questions and all that, where I try to be very careful. If I mean a vector, I will say a vector, or if I say get the tension magnitude, usually we're looking for the magnitude in these types of problems. So that's why I'm emphasizing the symbol for the magnitude here. mg. Now this other one we cover in chapter 13, that we're going to talk about in astronomical size problems. That's chapter 13. And then just to remind you, gravity is the force, but G is not gravity. What is G? G is related to gravity. It's the magnitude of acceleration due to gravity in free fall near the Earth's surface. So G is not gravity. And I want you to be careful. Just know there's a difference between a force and an acceleration. Okay. So I'm going to pause for just a second. I have no idea if this is sinking in at all. Any questions? Feel free. I'll grab a quick drink of water.
So what is the difference between a force and acceleration?
Well, this is skipping ahead a little bit. I was going to discuss this later, but since you asked, it turns out this might look a little scary, but it's not too bad. The net force, or the sum of forces, I don't know if you've used this symbol in mathematics yet. That's the summation symbol. So this just means net force it's another way to write. So basically you add up all the forces. It's not equal to acceleration. Think about it. The units. Let's do the units. I think that was Dom. So I'm going to pick on Dom. I hope this was Dom. Well, anyways, Dom, what are the units of force? Just remind me.
For normal?
Any force.
Newtons.
Newton, which is a kilogram meter per second. Are you okay with that, Dom?
Yeah.
Okay. So now look. What are the units of acceleration?
Meters per second squared.
So how do you agree that acceleration and force are not the same thing?
Because there's kilograms in it.
So what do you think I need to multiply by to make it work out?
You need to have a mass.
And that's the trick. And so we see, now think about what Dom just said. He says we need to have mass involved. You know this. If you push on a building with 100 pounds or 100 newtons of force, the building will not go anywhere. If you push on me with 100 newtons of force, I will fall over. And what I'm saying is this: the bigger the mass, the smaller the acceleration. Let me put it like this. So, click this other button. There we go. Almost lost the headphones. I guess a force was exerted on my headphones. Oh my gosh. Physicists are the worst, aren't they? There we go. Let's get this. So this gives rise to one of the more common misconceptions. This is actually Newton's second law, not his first law. So we'll just kind of jump ahead. I'll call this Newton's second law. It says the net force on an object is equal to mass times its acceleration. So to be clear, that's the net force. Sometimes you'll hear people say sum of forces. And let me check if that's visible on the screen here. Okay. So this is, physicists are lazy. That's just less stuff to write than all this. Now, if you push on a train, the train has an enormous mass. So let's say in this case, you have two situations. You could have the sum of forces is equal to an enormous mass. If you have an enormous mass, you would probably have a very tiny acceleration versus the same amount of net force. If you have the same size net force and you have a tiny mass, what should be true about your acceleration?
Should be large.
And so I just want to point out here, this was something that was kind of special back in the day, right? People used to think force and motion were related by velocity. People have like you probably have a misconception right now of thinking, oh, I need to apply force to get my velocity or to keep my velocity going. This is a common misconception. Most undergraduate physics students actually think force directly relates to velocity in their gut. They may know the equation, but then when the rubber hits the road and you ask them a question that exposes that, many students think that force and velocity are directly related. They're obviously related through the acceleration, though. So they aren't directly related. So you don't say the net force equals mass times velocity. It's mass times acceleration. And then you can go on and learn about velocity once you know acceleration. So I guess you could say it this way. Remember that acceleration, if I could say this another way, I'm going to cheat a little. Well, how about I say approximately equal to? Velocity change over time change, or let me just restart. Acceleration is like delta V over delta T, right? So acceleration relates to your change in velocity. And so forces can change your velocity. And that's maybe a good way to think about it. The bigger your mass, the smaller your change in velocity for the same amount of force, right? And Dom, I don't know if I addressed your question in a long-winded way, but is that kind of getting you somewhere where you asked about? Sorry.
Oh, yeah. No, it definitely did. So like, would we use force to like find, or can we use force to find acceleration, like at any given like mass or something like that? Or
exactly. Well, here's the deal. It's an equation. Just like any other equation, if you know two of the terms, you can get the third.
Yeah.
And so there's two general ways we're going to work this. Very well, I guess three. One way is you know the force and the mass, and you figure out the acceleration.
Yeah.
As an engineer, you might think a little differently. You might say, well, I know how much acceleration I want out of my motorcycle or my frog or my whatever, my Taco Bell burrito that I plan to throw at my children's face. Right? So if I know the acceleration I want and I know the mass, that helps me calculate how much force I need. So in the case of, say, a vehicle or something, let's say you have a spaceship and you want to get it to the moon. Well, you know what acceleration you need. You know how heavy this rocket's going to be. You're like, uh-oh, I need a lot of force.
So
yeah.
Force is like directly related to acceleration and indirectly related to velocity.
Yeah. And here's that relationship to velocity. You could say force directly relates to changes in velocity. Is that good?
Yeah.
Mm-hmm.
So wait, are we gonna, can we use, that doesn't relate to derivatives, right? Like, or does it?
Yeah, it does.
Does it? It does. So can you use force in derivatives and in calculus and stuff to like
There
go back?
go. Yeah. So it actually relates to the derivative of velocity, right?
Oh, yeah, which is acceleration.
So now let's get a little spicy.
Okay. I was thinking more like, oh, it's not the derivative of acceleration, right? Like it's derivative of velocity times the mass, right? You're just adding the mass in there, kind of.
Yeah.
Oh, okay.
Now I will show you a couple of things really quick. Now, if you are freaked out by seeing derivatives, it's okay. There's no derivatives in this class, but I just want to show you something because a lot of you probably are taking calculus right now, and maybe you're like, oh, I kind of know what he's talking about. So just watch this. Let's pretend for a minute there's only one force just to keep life easy. This symbol right here. Now, watch this. Let's say I want to understand how something moves. I need to solve this for V. Well, I'll just multiply both sides by dt, and I'll divide both sides by m. Notice that the change in velocity is equal to the force divided by the mass times a small change in time. Well, if I wanted to get the velocity, I could integrate both sides. And again, we don't have to do integrals, people, and we don't have to do derivatives. But notice this would actually give me the change in velocity is equal to the integral of force over mass times dt. So if I know how the force is changing in time, or the mass, right? And so notice if the mass is changing in time, this would also work. This would handle a spaceship where the mass is evolving over time. As it uses up fuel, its mass goes down. So that might change things. All kinds of complicated problems can be solved this way. And so in practice, what do you really do? You change this back to a sum. And you do it in a computer because computers can do sums really quickly and do numerical calculus. So it turns out you start here, do a bunch of work, and go down to there. And since we're at it, it turns out the quantity mass times velocity in physics is actually a thing called momentum, another vector. I don't know if you've noticed this, but a lot of the work that I'm showing on this board requires vector knowledge. That's why you're in this class, to learn the vector stuff so you can do cool stuff later, okay?
So is momentum, like, does it have to do with like how much force or like how much force you need to stop that object or something like that? Or like...
It's this. If you plug this in, this result is actually a better definition of force because this includes how the mass changes with time and everything. Turns out this equation is actually true in relativity, whereas this one is not. It turns out this is a better way to write force. So we say that changes in momentums over time relate to force, but basically it's the same thing. F equals ma. So this is the subject of your next course.
Why is that better? Is it more accurate or just a better
It's valid whether you're close to the speed of light or not close to the speed of light. Whereas this equation is not valid if your speeds are close to the speed of light.
Oh, so okay, so that works more for like everything?
Yeah, it's more general.
Okay.
Now, I can't remember. I haven't read Newton's Principia and all this stuff. I believe, if I remember correctly, so don't quote me on this, I believe this was actually the way Newton phrased it, but I might be wrong. He said acceleration of an object is the net force over its mass. But I hope you agree, this is basically the same thing here. All I did was switch the mass around. So yeah, this is Newton's second law. It's a really big deal. All right. What do you think? Any other questions? Sweet. All right, so let's go back to our screen share and see if there was anything useful in there. Okay, so friction, I'm going to use lowercase f, just showing you here. Sometimes I'll use capital F. And so capital F is kind of my coverall. If I say a force with magnitude F is applied, that's usually like a zombie or somebody pushing or pulling on a block. Spring forces are tricky. Spring force magnitude is Kx. We'll cover that more in Physics 161. There are electric forces. There are magnetic forces, strong and weak, and all these other things. And then at some point, I'm like, you know what? Let's just wait till you understand the basics before you go in to do all these things. A couple of notes here. Let's look at these here. So just be aware of this crap down here. I'm looking at the bottom of the page. For me, lowercase t is going to be time. Uppercase t is usually tension. And again, here I mean tension magnitude. Lowercase n is normal force. Capital N is newtons, the units. Lowercase f is friction. Capital F is some applied force. Push and pull are basically the same thing from different directions. And then notice this little comment right here. Usually we try to draw our pictures so that the magnitudes are positive because that's how our brains think, right? Normally you think of a normal force as positive. That said, you could do the math in this other way. And there is one or two rare occasions when we might think of a magnitude as being negative. But for the most part, I want you to think magnitudes are positive all the time. So think magnitudes are positive for this course, okay? Only in rare cases would you want a negative normal force or something. It's pretty unusual situation. All right, so we talked a little bit about Newton's second law right here. Let's see if there's anything I forgot. This. I want you to think of mass as inertia. The more mass or inertia you have, the more you resist changes in velocity. So your mass doesn't resist velocity. That sentence makes no sense. No one says mass resists velocity. That doesn't make any sense. You resist changes to your velocity. The more massive you are, the harder it is to stop you once you're going. Furthermore, the more massive you are, the harder it is to get you started if you're at rest. Okay, which kind of brings us up to this Newton's first law up here. And I just want to point out, read the last line first. This is basically included in Newton's second law already. Okay, so in Newton's second law, if A is equal to 0, you must have no force. Alternatively, if you have no force, you have no acceleration. Now, I should be clear. I mean, no net force. That's an important word. So you could have forces acting on you, but you can't have a net force acting on you. No net force. For example, right now, let's do this. How about I do this? I have some high class Vaughn's brand seltzer water in a can here. Hopefully this doesn't spill all over me. Right now, the acceleration of this is 0. That means the net force on it is 0. However, there are forces acting on it. What are the forces acting on it? If I can hold this level.
Normal force and gravity.
There's a normal force up and a gravity force down. And so those two forces must be balanced right now. And so there's no net force. Only the finest. Okay. Yeah, let's go back to that. So a lot of people, when they hear of Newton's first law, you always say, an object of motion stays in motion, an object at rest stays at rest. That's a good start, but it drives me crazy when people say that. It makes me just want to slap them with a fish. So let's get it right. An object in motion stays in motion unless it's acted upon by non-zero net external force. This is the part nobody ever says over here, but it's a hugely important part of that sentence to me, a physics teacher. All right, so an object in motion will stay in motion unless you act on it with some force. An object at rest will stay at rest unless you act on it with some force. Summation of those two lines is objects have constant velocity unless they're acted on by non-zero net force. So just be aware. An object in motion stays in motion, requires that extra little bit of non-zero net external force. All right. Let's call that good for right there. So that's Newton's. Go ahead.
Sorry, I had a quick question just to clarify it, even though like I'm pretty sure you already said this. So like net external force like has to equal 0. As in like other forces can still be acting on it, but it just has to be like balanced out. So like So like all those forces added together equals like 0 force, kind of, in like a weird way.
Okay. So right now, this is not lag. I'm actually not moving, except for my mouth, which never stops moving, as you've noticed. So right now, here I am. My acceleration is 0. So here's a picture of me. All right. So let's take a guess. Any guesses how much I weigh? Take a guess. I know you guys haven't seen me, but yeah, go.
195.
Oh man, you just got an A. So take a guess. You're too low. Okay, so 195. Any other guesses? Anybody?
None. 210.
210. All right, you guys both pass. Turns out I'm about 250 pounds. Can you believe that? More like 240 if I go for a lot of while.
Is it pure muscle?
Totally. Yeah, the tongue muscle is very developed from all this yakking on Zoom, right? No, but so let's say I have 240 pounds. Okay, and that direction is this way. So that's my weight. I'm going to call that the weight force, right? So another way to say it is I have mg, and that's equal to 240 pounds. Now, if I wanted to convert that to newtons, I could just quick go out to Google and figure that out and just type in convert 240 pounds to newtons. But for now, I don't really care about that. So now the floor, as I stand here, is holding me up, right? I'm not just magically levitating. I was going to do that later today. But so there's a normal force up. Whoops, I should be careful here. This is the magnitude. So and that's in the, that would be my normal force magnitude, the normal force that the floor is exerting on me. Now, if we wanted to write this out, the normal force vector would be 240 pounds j hat. The weight vector would be negative 240 pounds j hat. And so the net force on me let me just get this down here. The sum of forces would equal the normal force plus the weight force, which would equal 0 in the j hat. Actually, 0 everywhere, 0 in the I hat as well. But so the idea is, in this case, where my net forces, the force downwards and the force upwards, left and right, etc., everything all adds up, that tells me my mass times my acceleration has to equal 0. Since I know my mass is not 0, that tells me my acceleration is also 0. It's like the least interesting equation ever. But now, this is where we can make this a little bit spicy. So let's take a look at another example.
So can I ask a quick question about that?
Sure.
So the normal force was like the floor force?
The floor pushes up on me.
Really? That's kind of interesting.
Well, think about this. I push down on the floor, don't I?
Yeah.
So the reaction to that, there's another Newton's law. It's called Newton's third law, action reaction. We haven't gotten to that yet. We will soon. But yeah, that reaction to me pushing down on the floor is the floor pushes back up on me. Okay.
Okay. So like anything you're standing on that doesn't like break, it's like basically exerting like the same
even if it
amount
does
of force
break,
that gravity does in your weight.
Even if it does break.
Oh.
The problem is if it breaks, it wasn't big enough to hold me up.
Yeah.
So I just start accelerating downwards.
So even if it does break, it's still like at some point had an equal amount of force that it pushed back at.
Yeah. Imagine you swat a fly, right?
Yeah.
So a fly is flying and you swat it. You exert the same force on the fly that the fly exerts on you.
Oh, wow.
And you don't really feel it because you're so big, it's negligible on you because of your huge mass.
Yeah.
So because you have a huge mass, your acceleration is basically 0. You don't even notice it when you hit a fly. The fly, on the other hand, has such a tiny mass, it accelerates all the way across the room, smashes into the wall, and dies. So there's a huge difference when you have different masses. That doesn't mean the forces are different. Your accelerations are different. Your changes in velocity are different.
Yeah.
Got it?
Does that have to do with momentum? Like,
sure.
Well, yeah. Okay.
Yeah, let's leave that for later. Is that cool? You're asking great stuff.
Yeah, that's cool. That was really interesting. Fly. That was a very interesting fly example.
We're going to come back to that over and over and over again throughout the chapters and even into the next class. So
okay.
Let me give you another example here.
I have a question too.
Oh, go for it.
It's just to clarify, but the ground, the normal force is always pushing up with the equal force that you're pushing down with.
No. Oh, wait. Yes to that. Yes. So it doesn't necessarily match my weight, though. Sorry, that's what I thought you were originally going to say, and I interrupted you. So let me put it this way. If you put a box on here, let's do a quick example. Let's say there's a box in an elevator. Okay. Now the box, let's look at the forces on the box itself. So I'm drawing what's called a free body diagram. This is actually one of the first questions we're going to do. So that you're asking awesome questions, all of you. We know that there's an mg associated with the box. This is the weight of the box. You figure out its mass in kilograms, you multiply by 9.8 meters per second squared, and we would get how many newtons. Now there's a normal force up. If you've ever been in an elevator, you know that you feel a little weird sometimes in an elevator when it's starting or stopping. So for example, when the elevator starts going upwards, it's accelerating upwards. So let's think about this. Let's say you had an elevator that was accelerating upwards, right? Well, if I write this down, the force equations, I would say the sum of forces as vectors is mass times acceleration, right? That's Newton's second law. This is a pretty cool thing. So now let's do this. This force, well, I need a coordinate system. So let me draw my standard coordinate system. Usually we say X is that way, and usually we say Y is this way. So the normal force is going upwards. It's in the positive J hat. So wouldn't that be the normal force magnitude in the J hat minus mg in the J hat equals mass. Now, should I write positive A or negative A in the J hat here?
Positive.
Positive. And I've run out of room. So I'm going to just squeeze in the positive J hat right above there. Okay. The idea here is, what do you notice drops out of every term immediately?
The J hat.
Nice. And so if that drops out, I need to rewrite this. This thing basically becomes, from a practical standpoint, the normal force magnitude minus the weight magnitude is equal mass times acceleration. So notice, under what circumstance will the normal force equal my weight? Under what conditions in the real world will the normal force magnitude equal the weight magnitude?
When MA is 0.
Yeah. So if your elevator isn't accelerating, you feel your normal weight. If the elevator is accelerating, the ground is either pushing on you too hard or too soft, depending on which way it's accelerating. And so you feel heavier in an elevator when it's accelerating upwards. That doesn't mean you are heavier. You just feel heavier because your normal force goes up. And so the ground will always be pushing on you the same amount that you push on the ground. And so what we see is that amount is not necessarily equal to your weight. Think about it. This arrow has to be bigger than that arrow if you're going to accelerate that way. If you're going to accelerate down, this arrow has to be bigger than that. So the whole point of this is, well, if you're going downwards, so going back to Dom's example, he is saying, what if you're standing on something and it breaks? In that case, the normal force was insufficient to support your weight. You accelerate downwards. If you're in an elevator that's moving upwards, the normal force has to be greater than your weight for you to accelerate upwards. What do you think? Is this starting to make some sense?
Yeah, it's making sense.
All right. And so that's what and so what is the same, and I don't know who was asking this, is the normal force that the elevator exerts on me, right? So, or the box. So there's a normal force up from the elevator on box, but there's also a normal force down of the box on the elevator. So the idea is the elevator pushes up on the box just as much as the box is pushing down on the elevator. So that's true whether it's accelerating or not.
Does normal force always exist as long as there's like contact between two objects or something?
Pretty much, yeah.
Okay.
So, and in fact, we usually say if the wording in the problem says you're about to lose contact, that's an alarm bell that says set normal force to 0. So pretty much exactly what you said is good.
Okay, so let's say you had that pushed against, like a box pushed against a corner in a wall, would that vertical wall be having like a normal force going towards the wall, like from the box, and going outwards from the wall towards the box?
Okay, good question. So let's take a look. Let's say we have a box in an elevator, but this time the box is in the corner of the elevator. Now, when you stand up against a wall, let me put it like this. How about like this? Markers. Okay. I'm standing right next to this box. I don't know if you could tell that, but I'm standing right next to this. Now, I'm not leaning against it. I'm just standing next to it. how much, when you stand right next to something, but you don't lean against it, how much does it push on you?
If there's no contact, then 0.
Exactly.
It doesn't push you at all.
Exactly. Now, where things get tricky is if you did something like this. What if you lean? So this box, the wall would not do anything. But what if you lean the box? If you do this, you know from experience, if you lean the box against the wall, there's going to have to be a force pushing this way, and there's a force pushing that way. What's tricky is this doesn't always work because sometimes the box would slip. Aha, if you have this box that's not slipping, you get another force called friction. That's too hard for us right now. We'll deal with that next chapter. So it turns out you could have complicated sets of forces acting at multiple points on an object. And usually we go into this in depth in chapter 12. So I'm basically not going to answer your question any more than that. Is that cool?
Okay.
Yeah,
Thank you.
and we could do it in office hours if you want. But in general, you're absolutely right. Sometimes the wall will push on it if it's leaning against it. Now think, right? If the box leans against the wall pushes this way on the wall pushes that way on the box. The box is pushing downwards on the floor, it pushes upwards. There's friction this way on the box. That means there's also friction that way on the elevator. So it's very complicated. We haven't even discussed Newton's third law yet, but we're doing it every single problem. So that's cool.
Does normal force still like work the same with like other states of like solids or liquids or gases? Does it still work with like gases and
Liquids and
like
gases
that?
get tricky. We usually talk about atmospheric pressure or fluid pressure, and it turns out pressure relates to force in a different way. So there are similar forces, but we don't use normal forces with liquids and gases usually. We talk about
Okay.
pressure. Okay. Is that good on that?
Yeah, I'm all good.
All
Thank
right.
you.
Yep. All right. So I have a puzzler for you, everybody. I'm going to say something that's wrong, and I want you to tell me what I am saying incorrectly. Here it is. I think what we just said was, if you put a box in this elevator, anytime it's moving upwards, we expect that the normal force has to be bigger than its weight. Again, we said there's a normal force up, an mg down. We said this thing is going to accelerate upwards, and I said anytime it's moving upwards, the normal force has to be bigger than mg. Tell me what I said incorrectly. And Dom's been chiming in a lot, so Dom, why don't you try and give it a break just to see if anybody else chimes in for a sec, okay? Not trying to discourage you, just trying to mix it up. My claim, my incorrect claim, anytime this thing is moving upwards, the normal force has to be bigger than mg. One word.
The normal force, it has to be equal to mg, doesn't it?
Nope, that's close. You're on the right track. Maybe, kind of. Again, I'll say my sentence. Anytime this thing moves upwards, the normal force has to be bigger than mg. Something is wrong with that sentence.
Oh, is it the normal force times the acceleration has to be bigger than mg?
Okay, you're getting close. You're getting close. Look at this question down here. He's saying the normal force, something about acceleration. Okay, listen to my words carefully. Anytime this thing moves upwards, N has to be bigger than mg. What is wrong with the word moves? What symbol do we associate with the word moves?
Is it the sigma?
Say again, sorry.
The sigma?
Oh, nope. Sigma means net or sum of. Good guess. Good guess.
It's related to velocity.
Velocity. So be careful. The correct sentence is anytime this object accelerates upwards, n has to be bigger than mg. Now think. Describe a situation where you could be moving upwards, but n and mg could be equal. Is it possible to be moving if acceleration is 0?
Yeah, right.
Yeah. What would
If
be true
the-
about your motion if
If the
acceleration was 0?
velocity is constant.
Yeah. Sneaky, isn't it? You see where I'm going with this?
Yeah.
Check this out. When you're in an elevator, the first part, let's say you're sitting on the first floor. You know the elevator will accelerate, get to constant speed, then travel at constant speed, then slow down. So when you go in an elevator ride, at first, the elevator will be accelerating you upwards. N is bigger than mg. Then for a short period of time, you're moving at basically constant speed. It feels completely normal. You do a little dance like this. Then as you get towards the second floor, it slows down. It's actually accelerating the other way. If you're accelerating downwards, what should be true about your normal force compared to mg? If this arrow was flipped, which thing has to be bigger?
mg.
Yeah. So that means you feel less weight. Even though your weight hasn't really changed, you feel like you weigh less. So if you've ever been on the ride Tower of Terror, maybe you've experienced this. There's that Disney ride or something. By the way, I am not a big fan of Disney, but whatever. I have 2 8-year-old daughters, so I guess I do like Disney now. Anyways, yeah, and somebody dragged me on. Oh man, I just wanted to puke. I cannot stand rides. So anyways, yeah, they took the little photos and I was like green in the face, like about to barf. It was really bad. But the idea, why is that ride so interesting to people? It's basically an elevator that's going up and down, and they just rapidly change your acceleration. So your perception of your weight changes. People perceive their weight as their normal force, but the normal force is not your weight. Your weight is not changing. The amount of material in your body is not changing unless you puke. But other than that, we assume your mass is approximately constant. So as your mass is constant, your weight is constant, but the normal force changes as you accelerate up and down. Whoa, whoa, whoa. And so, yeah. And so, all right, the point of this was to remember that normal force is not the same thing as your weight. It relates to it through a force equation. Acceleration and motion are not the same thing either. If you move with constant speed, that's called dynamic equilibrium. So notice down here in this equation, if your change in velocity is 0, A goes to 0, N equals mg. So only when and so think about an airplane. If you've ever been on an airplane or in a car, if you're driving at constant speed or if you're on a bus at constant speed, right? Anytime you're on some sort of transportation where it's going in a straight line with constant speed, you could walk around and it feels pretty normal. Of course, if you hit a bump or something, you suddenly accelerate and you feel abnormal because your normal force is suddenly changing. But assuming you're going, like if you're flying in a plane in a straight line, you could walk around because you're not accelerating. You perceive motion when you accelerate, right? So, all right, let's leave it at that. Geez, we're like all over the place here, but this is good stuff. I don't know, any questions here? I'll go to the gallery view. I don't know, Jay, any thoughts you have for the crowd here? Anything you want to say about this? Okay, that's good. All right. All right, so let's take a look at the screen share. We got away from it. Let's see. And remember, all we're trying to do today is get a feeling for this. So hopefully you could actually read a book. Now, we are not in class, so this is kind of hard to do these demos. But I just can't do this stuff right now. This is a fun one, though. I usually do this every year. I think I have a video somewhere. I'll try and find it and send you a link or something. So you could actually put a broomstick on some wine glasses here and smash this. And this, or the tablecloth trick, maybe you've done this at home. And so I give you some instructions here. And I just want to point out, normally I do these in class and let students do it and break it. So you're kind of missing out, but we'll do them in 160. Well, 161 is gonna be online too, probably. So never mind. Sorry, let's move on. It just takes all the fun out of those. There's no point. Yeah, it is sad, but we'll blow some stuff up sometime. Let me see if I could show you something. I don't know if I have this still. At least you can laugh. You can make fun of me, and that'll be at least something you can get at it. We used to do the big science show that we're not doing right now. Oh, I'd have to go look for it and find the link. I don't remember where it is. So, but there's a funny, yeah. Okay, cool. Thanks, Jay. Yeah, so she's got it. And I do the tablecloth trick in there, and I do it in slow-mo, and I made somebody from the audience do it. It was really fun. I can't remember if I had the ones where we did it with the, yeah. So Jay's going to look for those links and videos. I know where I might have something. Let me try one other one here. Sorry, I didn't plan on showing these today. I wasn't thinking through. Let me try one more thing just in case. My hope is to eventually get all these demos up here. Oh, wait a minute. It's the wrong channel. There we go. Sorry it's taking so long here. I think I have one of these in here somewhere. Ugh, what a nightmare. Oh my gosh. This tells you what it's like trying to make a physics class online, people. Imagine making all of these stupid videos that are 9 seconds long. It's just dumb. Oh, here it is. There it is. All right, so hey, I bet I found the Friday Night Science too, I bet. But how do I copy this link? There it is. So if you want to see some of these demos, now I got to figure out where the chat is. So there's the broomstick on wine glass. That's a physics problem. 258 is a physics problem. Oh, yeah. So one of my former students, I said, oh, I'll put you in my workbook if you jump out of a plane, and he did. So that was kind of fun. No, that's not me. I'm not that crazy. So a former student of mine. So let's see if we have. Shoot, I don't know where that I don't know where that other one is. Jay, I don't know where that full video is. So yeah, if you're looking for it, that's cool. Anyway, gosh, this is just for like one part of one class, like a quarter of one class. Isn't that sad? Whatever. Let's get out of here and get back to work. So Jay's going to look for that other video there. Yeah, so that's actually, do you guys remember in that in chapter 2, or maybe it was, I forget what chapter that was. There was a story about a guy called Mr. Bonaventure who misspelled his name on his college application and got a scar that ended up looking like Harry Potter and ate the weird chips and couldn't recognize. The guy jumping out of that plane is Mr. Bonaventure. So yeah, that's a true story. He really misspelled his name on his college application. So yeah, it's kind of funny. But yeah, Hancock, now he's making a lot of money. He ended up doing material science, so that's cool. All right. I guess we're doing a little bit of partying today here. Zoom party. All right. I just want to point out something. Notice what we've been doing already. We basically just did this problem. And I want to point out, I did this problem two ways. One where there's a hanging scale, and one where there's a guy standing on a person standing on a like a normal bathroom scale. Okay. Now, to be clear, I want to point out there is a subtle difference here. In the upper figure, the object is accelerating downwards, and the coordinate system is upwards. Sometimes you might flip the coordinates like this. Now, a lot of you might not think there's a reason to do this, but I know what mechanical engineers need to know. And so I know eventually physicists, engineers all need to learn how to deal with weird coordinate systems. So it's not that I'm deliberately trying to punk you guys. I literally think this will help you understand stuff later. So even though this is going to seem really boring because we just did it, I want to do it again and notice the subtle differences between these. So we're going to look at these two problems, 5.3 and 5.4. Now, it is a little bit different that the acceleration is downwards instead of upwards. So let's try this out. What I want you to do is try and write down the proper force equation and then think about this. When will it equal the true mass? Okay, so I'm going to let you guys start on that. That's 5.3 on page 85. Okay. And while you do that, I need to look up one more thing here. Give me just a second. I've got a secret surprise related to that one. Where is that one? There it is. So after you finish 5.3, that was the reason I had that YouTube site open, was for this video. So let's look at 5.3 together now. Actually, I'll just do it up here. Now, I haven't really explicitly stated this, but what I'm going to draw right now is called a free body diagram, or an FBD. Again, what does that mean? Free body diagram. Okay. And the whole point of an FBD is to make the picture less confusing. What we are doing now is, instead of drawing the elevator, the scale, the string, the taco that's on the floor, the used gum wrapper, all we're doing is we're drawing the one body all by itself. It's a free body. It's all by itself. Okay, so what are the forces acting on this body? Well, somebody unmute. Tell me one force that is acting on this body. This is the ball in the picture in 5.3. What's one thing?
mg.
Mg. Which way?
Downwards.
All right. This is the weight magnitude. This is the weight direction. This is a vector when you put it all together. Okay, somebody else. What's a force that's holding it up? Or trying to hold it up?
The force of tension.
I would go with that. Sounds good. Tension. Which one should be bigger in this case?
They're equal.
Which way is it accelerating?
Oh, downward.
So which force should win?
So the gravity.
Yep.
Gravity
So
should-
then the tension should be bigger, smaller, or same about.
Smaller.
Okay, so let's draw it just a little smaller. Now, in practice, it's okay if you draw them the same and worry about that stuff later. But since this one's so easy, I kind of like it to at least try to draw the picture to scale. And what I did in all my workbook problems is whenever possible, I did all the math, calculated everything, and then drew the arrows approximately to scale so you get a feel for it. If you're an engineer, it's crucial to learn how to draw things to scale. Now, in this case, this was X, this was Y. It's accelerating downwards. So if you care, in the workbook solutions, I don't always do this, but I try to draw the coordinates and the acceleration in red. And notice this is going to be true. This is not a force. Acceleration relates to force, but it's not force. So you do not draw acceleration on the object. In a free body diagram, we draw the body and the forces. Next to it, you draw the acceleration and coordinates and everything, but you don't do that on the body itself. Okay? That's the whole point. We've seen basically from experience, students make fewer mistakes if they get this habit, and that's all of that is. Okay? It's not like it's the right way to do things. It's just easier to see stuff if you draw only the forces here. Okay. So now I'm going to write down my force equation. We always know the sum of forces is equal to mass times acceleration, right? That's always true. This is Newton's second law. Well, in practice, what we can do is we could split this off into a j hat part and an I hat part. And if you were doing 3 dimensions, you could do I hat, j hat, and k hat. So rather than write, just like we did with the velocities in projectile motions, we ignored the I hats and j hats. What I'm going to do now is write the sum of forces in the x without the I hat equals mass times acceleration in the x. Do you guys see any forces pushing left or right? Are there any?
No.
No. So what's the sum of forces pushing left or right?
It'd be 0.
How about the acceleration? How much acceleration do we have left or right here?
0.
So 0 equals 0. That's a pretty boring equation. Since I did that very difficult one, somebody else can help me here. So now I'll write down sum of forces in the y as mass times acceleration in the y. All right, so what's one force acting in the y direction? Somebody say it. Anything.
mg.
mg. According to the coordinate system, should it be positive or negative?
Negative.
Negative. So I would write negative mg. The negative comes from the arrowhead being opposite. You know what I'm saying? What's the other force? Somebody else.
Tension.
Tension, positive or negative?
Positive.
And I'm just going to sneak it in right here so it fits better. Okay, the order doesn't matter. Okay, so now all that's equal to mass. Now what do I write for the acceleration? What's AY?
Would it just be G?
Nope. G is only the acceleration if you're falling without any other force. G is called the free fall acceleration. So think about that. Are there forces other than gravity acting on this particular ball? Yes. So that means the acceleration is probably not G. Does that make sense why it's not G?
Yeah, that makes sense.
What did we say it was?
It's just the acceleration. It's just negative A.
Yeah!
Okay.
So the idea is I didn't want you to say A. The magnitude is A, the direction is negative J hat. So that's why we get a negative there. Remember, there's a J hat on all of this crap. Is that making sense, everybody?
Yeah, that makes sense.
All
Yep.
right. And so now at this point, I could write this down. This would be, if I solved for tension, let's just solve this for tension. Is that what I said to do? Solve the equation for the scale reading. Well, the scale reads the tension. Okay, so I'll just solve this for T. Factory net minus reading. So now we know an equation for the tension in terms of the acceleration and the weight. Under what circumstances would the tension read the true weight? Under what circumstances will T equal the true weight?
When the elevator is stationary?
Nope. Close. Now, while you are absolutely right that that is one of the possible cases, but that's not all of them. Does that make sense why I'm not saying full credit there?
Yeah. Also when it's moving at a constant velocity.
Yeah, that's what I'm talking about. So that's the most general way to say it. Anytime the elevator is moving with constant velocity or is at rest, that's a constant velocity of 0, then you're right. What circumstances would the scale read 0? Is that even possible?
When it's accelerating upwards like really quickly, right?
On the right track, though. Let the equation guide your reasoning. This is where it gets powerful. If I want T to equal 0, tell me something. What's the only way T could equal 0?
When it's accelerating at G upwards.
Not upwards. This one is A downwards. So in this case, when A is equal to think about it this way. When you accelerate upwards, it takes extra effort. The scale has to pull extra hard to accelerate upwards, right? If you want to accelerate downwards with rate G, what would that look like?
Then tension would equal 0.
Yes. Okay. I mean, like physically, what would that look like? Any ideas? I can think of one. It's the YouTube chat. The YouTube video I put in the chat. Whoops. Oops. Ah. Oh my gosh. Hold on. Oh my gosh. Whatever. My Zoom's doing some weird stuff. So that video I put in the chat is supposed to show you when you drop the thing and you let it free fall, the scale reading goes to 0. Another way you could see this, fill up a 2-liter bottle with water, poke a hole in the bottom and hold it up there. When you're holding it up there, the water's pouring out. If you stand on top of a ladder and drop it while it's in free fall, the gravity is pulling the whole thing down. So there's no need for the water to fall out. The water stops pouring out of the bottle while it's dropping. Similar type of scenario. But yeah, the point being is when you're in free fall, the scale reading goes to 0. So let me ask you this. When you're in free fall, when you're dropping, does your weight go to 0?
Your mass doesn't, but your weight does?
No.
No.
Your weight is still there. Your mass is still there. Your perception of weight disappears. So if you are in free fall, look at this. I was in free fall for a very brief time while I was in the air. This is not like a 1-second jump here. While I'm jumping up in the air, your perception is that you're weightless, but obviously you still weigh something. Otherwise you wouldn't be falling, right? So just watch out. Weight and perception of weight are tricky. Go ahead, Dom.
So is there like a relative force, like how we have relative velocity? or like is there like relative?
I don't like
Is there
to
like
think
anything
like that.
else? No. Oh, okay.
Yeah, that doesn't mean necessarily that mathematically you couldn't come up with something, maybe, but I don't know. I find that students have a lot of misconceptions about force, velocity, and acceleration, and I'm trying to expose those in our introductory lecture here. And so I would say this: by not thinking in those relative terms for force, I have built my own intuition that tends to be right more often than trying to think in weird relative ways. So I like to think of force in terms of what are the forces on something and just deal with it. And then you could worry about relative motion with relative velocity after the fact. Is that good?
Yeah.
Yeah, I avoid things like relative force. I can't think of a time I've ever used that. Yeah. Relative acceleration, maybe for a problem with kinematics, or relative velocity, sure, but not relative force. All right. Let's take a look here at the next one, and then we'll call it good today. So now I know you know how to do this, but let's just see what it's the same exact problem, but now the coordinate system's flipped and you have a different type of scale. All right, so let's see what this one would look like. Go ahead and draw it up. I'll draw mine up and we'll compare. Draw a free body diagram, write the forces in the y direction. And there's a purpose to this. I won't explain it till we're done. Do this together. Okay, I've got it written up. Okay. So now we've got this free body diagram. So we have some room here. I know we don't need the X direction, so I'm just doing the J hats only. So somebody tell me one force that this problem has in the Y direction. Give me one. I'm trying to fill out this side here.
Normal force.
Normal force. According to the coordinate system drawn, is it positive or negative?
Negative.
Negative. Okay, this arrow points opposite that coordinates. We're trying to get used to weirdo coordinate systems for reasons I'll tell you about later. Next, mg. Is that positive or negative? Somebody else?
It'd be positive.
Absolutely. So this feels a little weird, but that doesn't mean it's wrong. Just means you're not used to it yet. Okay, so here, mass. According to this picture, should I write positive A or negative A?
Positive A.
A, yeah. And so now I'm going to solve this for the scale reading. When I solve this, if I bring this over here and that over there, then switch the sides, I get this. I want to point out it's basically exactly the same as the last problem. we see that in both problems, the scale is supporting your weight. In 5.3, it was 0.4, it's pushing upwards, but it's an upwards force. And so in this case, N is the scale reading. And notice in both cases, whenever your acceleration is drawn downwards, regardless of how you do the coordinate system, you get the same result for the scale. That's a big deal. Listen to this right now. I know you're tired. It doesn't matter which way you draw the coordinates. The force equation should always work out the same. Now, you may get different minus signs when you start, but the final result for any one magnitude will be the same regardless, or it should be the same, regardless of how you draw the coordinate system. If your answer is not the same, that means you made a mistake. So that's a way you could kind of check your work with your friends. What if your friend chose a different coordinate system than you in a more complicated problem next semester? Well, you know that the coordinate system shouldn't matter. You should still be able to compare final answers for questions. And that was a big deal. This was actually one of the fundamental postulates of special relativity. So Einstein's big deal with special relativity, there were two things. He said, one was nothing goes faster than the speed of light. And the second one was coordinate systems shouldn't matter. That's pretty crazy that he came up with all that crazy stuff about space and time from those two things. One of them was so fundamental, it was coordinate systems shouldn't matter to the physics. That's a big deal. All right. A quick summary with our last minute. Notice in all these equations, we're going to write sum of forces in the X and sum of forces in the Y. The arrows contribute to this side. So we use the arrows on the free body diagram to tell us this stuff. The coordinate system relative to these arrows tells us the plus minus signs. And then acceleration here could be plus A or negative A, but in practice, we usually choose a coordinate system such that it's positive, just so that I don't accidentally forget the minus sign. And that's a pretty good summary for today. Let's call that good.